Hi, my name is Ben Gerard, and today I'm going to go over plasma frequency and cyclotron frequency. So first I'm going to give a little overview of what I'm going to talk about. I'm going to start off by talking about plasma frequency, as well as its significance in studying plasmas. And then I'm going to talk about cyclotron frequency and its significance in the study of plasmas. And then I'm going to do a little example calculation on how to find the plasma frequency and cyclotron frequency of a system, particles in a system. And then finally, I'm going to go over how to tell if those particles are magnetized. So first, as I said, I'm going to talk about plasma frequency. Plasma frequency is the natural frequency at which electrons in a plasma oscillate when disturbed from equilibrium. It is calculated using the equation shown in the slide, which is basically the square root of the charge of an electron squared times the density of electrons divided by the vacuum permittivity and the mass of the electron. As you can see, because the charge of an electron, the mass, and the vacuum permittivity are all constant, this equation can be simplified into the two equations below. The plasma frequency is significant when studying plasmas because it defines the response time of plasma to disturbances, and it determines whether an electromagnetic wave can propagate through. If the electromagnetic wave frequency is below the plasma frequency, then the plasma will reflect the wave instead of propagating through it. So now I'm going to talk about the cyclotron frequency. The cyclotron frequency, or another name for it is the gyro frequency, is the angular frequency at which a charged particle orbits in a circular path within a uniform magnetic field due to the Lorentz force. This is calculated by the charge of an electron times the magnitude of the magnetic field divided by the mass of the particle. This can be calculated for different particle. It can be calculated for both electrons and ions. This value is significant in the study of plasmas because it stays constant regardless of speed or orbit radius or any other value besides the magnetic field and the mass of the particle. And it is a fundamental property used in plasma confinement, particle acceleration, wave particle, and basically all of plasma studies use the cyclotron frequency. So the example I'm going to go over is a xenon Hall thruster. To start with, I listed a couple of the properties of this plasma, of the xenon plasma. As you can see, when we plug in our values, the plasma frequency comes out to be around 6.1 gigahertz, and the cyclotron frequency of the electron comes out to be around 1.3 gigahertz. Typically, the plasma frequency will be larger than the cyclotron frequency. We also I also here calculated the cyclotron frequency for the ions. As you can see, it is much at 5.9 kilohertz. It is much, much smaller than the frequency of the electrons. Finally, the last thing we're going to go over is how to tell if the electrons and ions in a plasma are magnetized. One method of determining if the particles are magnetized is by comparing their Larmor radius with their mean free path, as well as the length of the channel that the particles are moving in. So when we compare them, we find that particles are magnetized if their Larmor radius is significantly smaller than their mean free path, as well as the length of the channel. For our example, let's set the length of the channel to be around 1 centimeter. Using the properties from earlier, we find that the electrons of this Hall effect thruster are magnetized while the ions are not. And because of this, the electrons will get trapped or confined in the magnetic field, while the ions will not magnetized, will freely move out the end of the channel. Thank you.